Hello, this is class number 5 video lecture, and we're going to cover sections 3.1 through 3.2, which deal with nominal and effective interest rates. First, I want to lead you to the start page in Blackboard, where you should check out the course schedule of assignments, because these will change from time to time depending on how much progress we're making and other factors. You should read pages 79 through 86 in your ebook or your smart book, whichever you prefer. And the third year, the instructor video, this one that you're now watching, is you're responsible for it. And in this video, I'm going to cover these lecture notes, which will be posted online under Module 3, which deals with Chapter 3. And there'll be other videos posted in this module as well. So the effective interest rate is given the symbol I. And as you recall, in every one of our interest rate formulas, we used I for the interest rate. That is the effective interest rate, and that is the only interest rate that'll work in those formulas that we presented. You'll probably get away from actually calculating the formula values, but it's very important that whether you do the calculations, whether you look them up in a table, whether you do have a programmable calculator, or if you use what I prefer is the Engineering Economics Career App, the interest rate that you have to enter is the interest rate I. Now, the author talks then about other names for these rates and other kinds of rates. For a lot of consumer finance documents, they use the term the annual percentage rate or the annual percentage yield. So APR for annual percentage rate, APY for annual percentage yield. Now the annual percentage yield is the actual I value. It's the effective interest rate. The average percentage rate is not the effective interest rate. It's the nominal rate. We use the symbol R to represent the nominal interest rate. It's kind of like the interest rate in name only, because it doesn't go in those formulas. The I has to go in the formula. So we're going to talk about the difference between these two rates and how you deal with that difference over time. So we're going to talk about 3 types of problems. The type 1 problem is what we've been solving up to this chapter, and that is where the compounding period equals the payment period, the period of the cash flows. And so when that is the case, then you're in a type 1 situation, and you just plug in the effective interest rate into the formulas to get the right answer, so to speak. A type 2 situation we're going to cover then in today's lecture, and we'll cover type 3 in the next lecture. But the type 2 situation is where your payment period, your cash flow period, the period between a uniform series or a gradient series of either type, the arithmetic or the geometric, the period between those payments is actually let's see, it's less than it's greater than the compounding period. So a situation would be where your say interest, where you're making, let's say, payments only once a year, but the interest is getting compounded every month. So the payment period would be yearly, and the compounding period is monthly. It's much shorter. So that would be a case or type 2 situation. The next thing we're going to talk about then is some formulas that can convert us from a nominal rate to an effective rate. But in order to do that, that's going to be in equation 3.2, we have to first get the nominal rate for the right period. That is, we have to get the nominal rate for the same time period that we want the effective rate. Now, the nominal rate is nice and easy to work with. You just do the mathematical calculation that, whether it's multiplication or division, that is logical. For example, if you want the nominal annual rate, as I show here in equation 3.1, you're given the nominal monthly rate, you just multiply it by 12 because there's 12 months in a year. If you want the nominal monthly rate, but you were given the nominal annual rate, you just divide it by 12. Similarly, if you wanted the quarterly nominal rate and you had the monthly rate that is nominal, you'd multiply by 3. And similarly, if you wanted our monthly, but you were given our quarterly, you just divide it by 3. So you can convert from 1 hour period to another hour period by just doing the multiplication or division. Now the next equation is the effective interest rate formula. And that formula says the effective interest rate, I, for any period, you decide at what period you need it for, is equal to 1 plus the nominal rate for that period divided by m to the m power minus 1. That's equation 3.2. That's the formula for the effective interest rate. What is m? M is the number of times the interest is compounded in the period for I or R. Remember, I and R must have the same period in this equation. So, for example, suppose we have quarterly payments. That is, the payment period is quarterly. Therefore, we need I quarterly. Suppose the rate given is 12% per year, compounded monthly. So the compounding period is monthly and the payment period is quarterly. So this is a type 2 situation. You always need the effective rate for the period between the payments or the cash flows. In this case, you need I quarterly. So to get I quarterly, we first go back to equation 3.1 and find R quarterly. R quarterly is equal to R annual divided by 4, right? There's 4 quarters in a year. We were given R annual is 12%. Why do I know that's an R and not an I? Because it's per year, but it's compounded monthly. If it was compounded per year, that would be the effective annual rate, but it's not. It's compounded monthly. So we divide that 0.12 or 12% by 4 and get 0.03 or 3%. So that is our nominal quarterly rate. Remember, the reason we got that was because we want the effective quarterly rate. So I quarterly is equal to 1, this is equation 3.2, 1 plus R quarterly to the divided by m to the m power minus 1. Now, remember, m is the number of times the interest is compounded in this period for R or for I, because they have to be the same period. So how many would that be? Well, there's 3 months in a quarter. Remember, not 4 months. There's 4 quarters in a year, but there's 3 months in a quarter. So m is 3. So we would plug in, remember we got R quarterly was 3%. We want I quarterly, it's 1 plus 0.03 divided by 3, that's 3 months in a quarter to the 3 power minus 1. When we crank through that, we get 3.03% per quarter. So that is the effective interest rate that we must use to solve a problem where the cash flows were quarterly. And so we'll go into that in the next section. In section 3.3, we're going to talk about reconciling the compounding period with the payment period. And in particular, we're going to deal with type 2 situations in this class. And so, as an example, suppose you have deposits into an account on a yearly basis. So that is your payment period. But the account compounds interest every quarter. That's your compounding period. In this case, your deposits or payments, PP, is annually, but your compounding period is quarterly. So the payment period is greater than the compounding period. And this is called, as I said, type 2 situation. And another possible situation is where the opposite is true. Here you make monthly payments into an account that is compounding quarterly. Now your monthly payments are monthly, but your compounding is quarterly. So the payment period is quarterly, compounding period is monthly. In this case, the payment period is less than the compounding period, and that's a type 3 situation. We'll cover that in the next class. The next thing I'm going to do is work some homework problems. This first problem is a problem in more than one sense. It's I could not reconcile the answer in the back of the book, so I'm going to give you the answer that the author gives, even though I think it's wrong, but I'm going to work the problem correctly and give you my answer as well. So that's what we're going to do with problem number 1. This is part of your grade now because it's directly out of the Smart Book homework problems. You have a very good yearly salary and a smart investment manager. She tells you that in only 6 years, you can accumulate $688,530 from quarterly deposits of $20,000 into an account that has a historical return of 12% per year, compounded quarterly. It seems like a stiff commitment, but one worth trying as you prepare for an early retirement from your current defense contractor engineering job. Now note, this is a multi-part question, the author says. Only once an answer is submitted, you will not be able to return to this part. You are a cautious investor. Suppose the market does not perform as your investment manager predicts, and that the return is only half, 50%, of what she predicted. Remember, she predicted 12% per year compounded quarterly. What is the future value of your quarterly deposits? Well, in this case, we have compounding quarterly and we have payments quarterly, so they're really aligned. It's just a matter of using the correct interest rate and defining the problem properly. Now, the smart investment manager had the historical return of 12% per year compounded quarterly. You are making quarterly deposits. Therefore, you would need the effective quarterly rate, I quarterly. So that's the rate we need. But the rate earned turns out to be only 50% of the predicted rate, or half of 12% per year, 12% per year, or 6% per year compounded quarterly. You made quarterly deposits of $20,000. So that's your uniform annual series or quarterly series. A equals 20,000, and you did that for 6 years, so there were 24 of them. So N equals 24. what is F, the future value? So that's what the question is looking for. You have your I quarterly, well, you don't have it yet. First find R quarterly from equation 3.1. So we were given 12% per year compounded quarterly. So this is an R, 12%. So if I want R quarterly, I just take R annual and divide it by 4. So although it was predicted to be 12%, it was only half that, so it was 6%. So we divide 6% by 4 to get 1.5% per quarter. That's the I quarterly, that's the R quarterly. Now, what's the I quarterly? Well, we plug into equation 3.2 to get the I. It turns out that it's compounded quarterly, so so M is 1 in this equation, so we will get 1.5% again per quarter. So in this case, the I quarterly equals the R quarterly because it's compounded once in a quarter. Now use the Engineering Economics Career app to find the future value of N equal 24 quarterly deposits of $20,000 at a rate of 1.5%. So I get F equals A, F given A, I, and N. 20,000, F given A, 1.5% per quarter, 24 quarters, $572,000. However, this is not the way the author solved this problem. The author did the following, and he came out with, he got the effective annual rate, and then the author uses 1.68% per quarter. That makes no sense whatsoever to me. But that's the way the author did it, and this is the answer that the author gave me as an instructor. I get to see that first, and I think it's a wrong answer. So when you work this problem, I suggest you put in that answer because you want to get credit for it, even though it's wrong, but work it the way I did, okay? Understand at least working it the way I did. I'm going to work 2 more homework problems for you. Problem number 4. Fortunately, the author got these right in the answer key. Julie has a low credit rating, plus she was furloughed from her job 2 months ago. So she's been out of work 2 months. She has a new job starting next week and expects a salary to start again in a couple of weeks. Since she is short of funds, money, to pay her rent, she decides to borrow $120 from a loan company. Bad decision. Which will charge her only $10 interest. Okay? If the $130 is paid no more than 1 week after the loan is made. So for having a present value of $120, she's going to accrue $10 in interest in 1 week. So that's her future value. This is her present value. N is 1 week. So what is I? So if we do this and work through it and solve this equation, F is equal to P times 1 plus I to the N, where N is 1 week. Okay? Solve that equation for I. We get I equals to 8.33% per week. This is both the effective and nominal weekly rate. To get the effective rate, really effective annual rate, we always use equation 3.2, or to get any effective rate, you use equation 3.2. So I per period is equal to 1 plus R per period over M to the M power minus 1. Well, in this case, we want I annual. What is the effective annual rate? it's equal to 1 plus the nominal annual rate divided by m to the m power minus 1. Well, what is m now? Well, we're dealing with weekly, right? So m is going to be 52 inside a year. And then what is r? Well, r is going to be, our annual is going to be 52 times our weekly. So we'll multiply that times 52. We'll use the decimal equivalent. So our annual equals our weekly times 52, which is 4.3333. Okay, 0.08333 times 52 gives me that number. And then I want the effective rate. Well, I'm going to get 1 plus this divided by 52. There should be a slash here. Divided by 52 to the 52nd power. That's 1 plus r over m to the m power minus 1. Turns out that this is 63.214, and that is 6,321% per year. Okay, so we're going to work one more homework problem, and then hopefully that'll put you on a good track to finish up some of these other homework problems. Metal fab pumps and filter expects the cost of steel bodies for 6-inch valves to increase by $1.25 every 3 months. If the cost for the first quarter is expected to be $80, what is the present worth of the cost for 3 years time period at a MAR of 6% per year compounded quarterly? So the first cash flow is $80, and it increases by $1.25, $80 each quarter. What kind of a series is that? That's a combined series. That is a uniform series plus an arithmetic gradient series. We need the effective quarterly rate, I quarterly. Well, I quarterly is equal to 1 plus r quarterly over m to the m power minus 1. That's equation 3.2 again, okay? It's 1 plus 0.015 over 1 to the 1 power minus 1, which is 1.5%. Again, since we can convert from one quarterly period to another, we just divide that by 1.5. But that's also the per quarter, and we want the quarterly rate, so the effective quarterly rate. But since it's compounded every quarter, m is just 1, it falls out very easily. We have a combined series with a equal to 80 and capital G, the arithmetic gradient, equal $1.25. It occurs every 3 months or 4 times a year for 3 years, so that's 12 cash flows. So n equals 12 quarters. N is doing double duty for us, by the way. Whenever we have a series, it's counting the number of elements in the cash flow series, and it's also calculating the number of compound interest periods. The question asks for what is the present worth. Okay, so P is equal to 80 times P given A, 1.5% for 12 quarters, plus the gradient series part now, $1.25 P given G, 1.5% for 12 quarters. If we calculate this out, we get $945.17, but we don't probably need that. It's $945. And that concludes class number 5.